Yes, it kind of looks like there's a spider sitting on top of my head, but that's from my drawing from the previous video. Finally get to use it a little bit to let you know what we're going to be doing today. But a quick review first. So just that we're on the same page, we were looking at 3 key areas or topics that we're going to cover regarding the jumping spider and the importance of these 3 areas that are essential for the spider to be able to capture its prey and survive. And those 3 areas were excellent eyes, which we covered last time, and number 2 is going to be the hydraulic legs of this spider, or the hydraulic system behind those legs. That's what we're going to cover today. And the 3rd area is a ballistic brain, and we'll get to that next time. Now, my little drawing I did for you last time, I want to talk about it today and use it as referencing the areas we're going to discuss. Now, so you understand the diagram or the picture, I have here a nice sharp knife. And this will help you understand what you're looking at, because it's not a spider with only 4 legs. Just think of it this way. If I take a nice sharp knife and cut the spider right in half, from top to bottom, that way you're going to see just half the spider. The other half's laid open so you can see what's inside. That's why you only see 4 legs on this split view. Since we're going to be talking a lot today about the blood of the spider, these colors on the diagram might help you. We're also looking at the nervous system of the spider. So, can you guess which color would be the one that's for the heart? If you guessed red because of red blood, no, that's this is a trick question, obviously. The red or pink area is actually the whole nervous system. And in that system in there is the brain, which we'll get to next time. But in actuality, we're going to be looking at the heart. And the spider's blood, known as hemolymph, is what flows through its body through a structure that is unlike the human blood, which is red. And it's blue because that's the color of a spider's blood, as their blood contains a copper base, and it's full of protein and minerals and sugars and enzymes and various things, a little bit different than our blood, but similar in other ways. This cutaway portion of the drawing leaves out things like the reproductive organs and some other organs and muscles, etc., that are not important for what we're talking about. But you might ask yourself the question, what about this heart? I mean, look at it. It is not like the heart you might expect. It is long and tubular and stretches from the head carapace area all the way down into the back of the abdomen. In humans, the arteries, the veins, etc., are set up as a closed circulatory system. It is a form of hydraulics. And the spider's is similar. It works on a semi-hydraulic system. In other words, its blood is always under pressure. And it's used that in a special way. It's the only animal that uses this particular hydraulic means to make jumps. That's right, jumps. Because you see, grasshoppers have jumper legs. Humans have muscles in their legs to help them jump, but the spider doesn't have muscles in its legs to help it jump, other than to bring its leg in. Okay? It's called flexing. When a human flexes his arm or leg, you know, we pull it in. It's a muscle in the arm or leg that causes us to flex the muscle, arm or leg, inward. To extend it outward, we have a different muscle that does that. The spider does not have the extension muscle at all. It can only pull the legs back in. So what pushes the legs out? Haha, glad you asked that question. Let's talk more about this hydraulic system. Back in 1959, when I was 9 years old, out hunting in the prairies with my mason glass jar and lid, there were some wonderful studies going on by two very interesting persons involved in the study of arachnids. And their names were Parry and Brown. And back then, they did some amazing studies on this hydraulic system the spider uses to make its jump. Now, there's been several studies that have been done down through the years, some of the latest back in 2010, 2015 even, and I think some even later than that now, that study the spider's jumping abilities and this the ability this spider has to launch itself. Depending on its size, it can launch itself 10, 20, 30, 40, even 50 or more distance of its own body, which is incredible. That takes incredible force and pressure to make that happen. The velocity of the spider's blood, which is its fluid, which is why it has the same dynamics as a fluid in a closed system. By the time it gets squeezed into that small tubular leg, that leg goes woo! And just stretches right out, wham! And that spider can be launched with great pressure produced in the leg to extend it straight out. That's how the system works in the spider. Pretty amazing stuff. Oh, hi neighbor. How are you doing today? Now when it comes to the Phidippus audax spider, and there's some others like the Regus, that the jumping spider uses its third and fourth leg when it makes its jumps. The front sets of legs, they're actually raised up off the ground when it prepares to jump. So the only legs that are on the ground are this third and fourth set of a jumping spider's legs. Now, some spiders use the third pair of legs, some spiders use the fourth pair of legs. Some use a combination of both legs. And I left this blue here to show you that this is where the blood goes down through that leg. That would be the third pair, or this one, the fourth pair. Here's how this works. Our system in human beings is a closed system I mentioned. We have arteries and capillaries and veins that flow the blood through the body, bringing oxygen-rich blood to the various organs and parts of the body. That's how the human works. Not the same in the spider. It doesn't have that complex artery, capillary veins working in its system as a closed piping system, if you will, of hydraulics. No, but it works very similar. That's why it's called a semi-hydraulic system. Let's take a look at the drawing again. There are main arteries or channels, if you will, tubing, if you will, that carries this blood, this hemolymph, to various parts of the spider's body, just not in the complex tubes that we use in our body. Got some main tubes. Legs are one. By the way, this spider is always under pressure. And when it runs or jumps, that pressure can increase 10, 20, 30, 40, 50 times the pressure that it normally uses just to walk. Not a whole lot of pressure is needed in its legs when it's standing still or slowly walking. But if it runs or jumps, then that pressure dramatically increases and it creates the ability for those legs to move quickly. There's cavities and tissue sections within the body that have spaces. And in the spider, this works in the head area, the front part of the spider. That's where the carapace is, the shell that goes over the spider's head. It's where its fangs are. It's where its venom glands are. And it's where its nervous system is. The back part of the spider is the heart. Okay? And it can come up into here and intermix with various things. Like it's got tubes that go down to each leg. Now, here's how this whole thing works. This nervous system causes muscles and things in the head area to contract. And when it does that, it creates an instant loss of pressure, resulting in blood to come in and fill those areas. And then when it needs to, such as in a jump, it can release that and it will surge through the various piping down the legs and cause those legs, remember, that only can be pulled in, that can't be pushed out. Well, in the first joint of these legs, there's a special, unique joint that has a very interesting twist dynamic to it. And when this blood pressure surges and pumps that into that leg, it twists that special joint and stretches that leg out in a nanosecond. As soon as the pressure is released by the brain to go into the system of the spider's legs, it's almost instantaneous. And those legs just stretch right out, launching that spider into the air. Now, to give you just a little science experiment explaining what this means, because there are laws of fluid dynamics, and we're looking at mass fluid. And so there's a law for that, and this is how it works. I have a little pipe, and the pipe is about the same size as the hole in the top of the bottle. Now, with the law of mass flow, it wouldn't matter if I squeeze with the same pressure on this bottle. The flow that came out here would be the same if I put in this extension tube and pushed the same pressure again, even though I had a further way to travel. Because it's in a closed-in system and closed pipe here, it's going to come out with the same force that it would coming out of the top of the bottle. You get that? Do I have to get myself all wet to prove that to you? Yeah, probably do, because you want to see me get wet. It ain't going to happen. But let me just show you. If I squeeze this, okay, it's going to take a while to get up there. Oh, see, there it comes. I survived. If I pull that out and do the same pressure type on the bottle, yeah, same thing. No change. Now, you might recall in a couple of videos earlier, we were talking about hydraulics and the spider and how hydraulics works. And it's different from gas, which can be compressed, but liquids, water or oil, cannot be compressed. I'm just going to put this nozzle on top and shut it tight. And now you can see how the opening goes from here to little tiny here. So what's going to happen? Oh yeah, as the flow continues, because the flow with the pressure has to be constant, that won't change. But as it tries to squeeze through the narrower area, it has to speed up in velocity, because the pressure changes with nothing changes in the pressure nor in the flow except the velocity. So here's what this looks like. Why am I saying all that? I'm saying all that so you get what happens in this spider's body. Well, all this flows quickly through here, down, you see, now going larger tubing down to smaller tubing of the leg and down to the bottom of the foot. Same thing happens over here in this leg. This would be the fourth leg. This would be the third. Now that's kind of a rudimentary overview of how that system works. It's actually quite complex. And next time, in the next video, we're going to talk about the brain, because it's the brain that has to coordinate. Anyway, all this. Enough education. I hope that's helpful. And now we're going to go take a look at what Judy's been up to. And in the process, I caught myself another spider, another female, probably about a year and a half old, who has all three of those capabilities functioning quite well. And she knows how to grab a fly and can. Judy, on the other hand, is struggling now to eat. And we'll talk about that. Oh, this will be interesting. She's going to step right on top of the fly. Oh, it's not funny. She just can't see. Poor girl. Well, that was interesting. Judy, you walked right over the top of the fly. You can't eat doing it that way. Oh, boy. No, you stay in there. You go get your fly. You need some protein, girl. Sometimes blind people use a walking stick. Judy just uses her two front legs, so she's got two walking sticks trying to figure out what's in front of her. Judy, Judy, why don't you go eat? Well, your cholesterol looked pretty today in the sunlight. That's a good thing. And you got a lot of energy. You just have to find that food.
Well, Judy has not eaten a fly for 4 days. So I was basically giving up on her. However, today I decided not to mess with the thread, but went right in with one on a tweezers. And she wasted no time touching it once, grabbing it the second try. She's got that fly in her jaw and fangs, and she's will be enjoying a nice meal for breakfast. This girl just baffles me. Good for you, Judy. You're still amongst the land of the living and doing quite well at it. Okay, the tweezer will be the new procedure to feed Judy. I came in this morning with a tweezer and a fly, and she grabbed it in 3 seconds. So I'm doing away with the thread business and going right in directly with the fly for her, because I think she figured out that I can deliver a fly to her and she doesn't have to sit around trying to chase a fly on a string.
Wow. I'm going to take her out for a nice outing in the backyard. Beautiful sunny day. She'll love it. Hey, thanks for watching. We'll catch you next time. Have yourself a great day. Take care now. I got Judy out here. We're going to go for a little walk. Right, Judy? Yeah. You and me, we're going to go for a little adventure in the yard. Look at that. I just love that carapace. That head looks like you're wearing a Darth Vader helmet. Oh, you're going to stare at the camera. Yeah, do you know what you're even looking at? Probably not. But that's okay. Yeah. Look at you. You're so cute. That sunshine feel good? What you doing? Backing up on the stick? Oh, you're trying to lay some webbing. Yeah, you be careful. You don't have any webbing, girl. You have no webbing to lay down there, so you have no lifeline. Be real careful, Judy. All right, let's go take a little walk.